Welcome back to the grand finale of our weekend data story. Today, two layman data engineers are cracking open the ultimate black box, the real-time fraud detection pipeline. And to understand the sheer engineering precision required here, we need to set the scene. It's 3 a.m. and you are fast asleep in your apartment in Mumbai. But 4,000 miles away, a hacker is standing at a slightly worn ATM in Moscow. In the exact millisecond he inserts a perfectly cloned copy of your credit card into that glowing reader, a massive invisible clock starts ticking. Your physical bank card is safe in your wallet, but the magnetic stripe data has been compromised. More importantly, this hacker has your correct PIN. The traditional frontline physical security measures that rely on passwords and plastics have already failed. You are completely vulnerable. You're asleep, unaware that your bank account is about to be drained. You can't call your bank to stop it. The system has to act entirely on its own, with zero human intervention. Security has moved from the physical keypad into the invisible data architecture, operating in the milliseconds between that card swipe and the cash dispenser. This is where the real defense happens. Look at this animated diagram to see the absolute engineering constraint we are dealing with. We have a digital countdown timer suspended over a connection between Moscow and a central bank server. It starts at exactly 3 seconds. This is the 3-second service level agreement, or SLA. From the microsecond that Moscow ATM reads your cloned chip, a data packet must travel across the globe to the bank's network, be ingested, analyzed, scored for fraud, and an approve or decline command must travel back. If this round trip isn't completed before that 3-second network timeout, the connection drops. If the bank's processing system lags out and misses that tight deadline, the ATM protocol typically defaults to a standard approval. The cash drawer opens, your money vanishes, and the bank eats the cost. The bank's infrastructure processes millions of concurrent global transactions in this exact same window, each one demanding its own 3-second countdown. To survive this kind of pressure, engineers abandon traditional monolithic systems and rely entirely on a highly specialized, decoupled data engineering pipeline. At this scale, network latency and processing bottlenecks are the primary enemies. If you are slow, you are compromised. Let's track the data. The ATM creates an initial payload. It packages your 16-digit card number, the Moscow location data, the withdrawal amount, and a precise timestamp, encrypts it, and fires it over the network to the bank. Immediately, we hit our first major architectural bottleneck. On Black Friday, traffic can spike to 10,000 transactions per second. Writing these incoming payloads directly into a standard database would cause the server to choke, lock up, and crash. You need a buffer. That is why the very first layer this data packet hits is Apache Kafka. Kafka acts as a decoupled ingestion buffer, sitting squarely between the fire hose of incoming data and the internal processing systems. This animated diagram shows the data moving like cars through a multi-lane toll plaza. Thousands of glowing dots, representing our data packets, fly through the open gates without stopping. Kafka doesn't inspect the contents. It instantly sorts them into distinct, parallel lanes, which we call partitions. Zooming into one lane of this append-only log, transactions align in sequence. Kafka accepts the payload, applies a timestamp, and queues it. This publish-subscribe architecture guarantees that even if the bank's internal compute servers slow down under a holiday load, the incoming ATM data is safely held in memory. Nothing is dropped. Separating ingestion from processing is the only mathematical way to absorb massive surges without breaching that 3-second SLA. So Kafka has caught the Moscow packet and queued it up. Now it hands the payload off to the brain of the pipeline to determine the next move. This brain is the stream processing compute layer, typically powered by extremely fast stateful frameworks like Apache Flink or PySpark streaming. Flink immediately runs the packet through the rules engine for simple binary checks. This animated diagram shows the packet hitting a fork, incorrect PIN, and zero balance. If those trigger yes, Flink kills the transaction instantly. But our packet passes straight through the middle, with green checkmarks all the way down. Our Moscow hacker has a perfectly cloned chip and the correct PIN. His account balance is fine. The stateless rules engine can't catch the theft because the inputs are technically valid. To catch a valid-looking transaction that is actually fraudulent, Flink triggers a machine learning model, but an ML model requires historical context to evaluate current behavior. Stateless processing catches mistakes. Defeating a professional hacker requires stateful context. We have to look at the past to validate the present. The ML model demands your habitual geographical locations, your purchase history from the last 24 hours, and your standard spending profile. You might be tempted to run a standard SQL select query on the bank's main customer database to pull that info. That's a mistake. This split-screen comparison reveals the mechanical failure of traditional SQL at this scale. On the left, performing complex table joins and disk reads across a relational database takes hundreds of milliseconds. Burning that much time just to read data is a fatal compromise for our SLA. This is why the stream processor instead queries a NoSQL database, usually Apache Cassandra or Redis, like you see on the right. These databases solve this specific read latency bottleneck. Instead of relational joins across multiple tables, Cassandra stores your user profile as a single, flattened key value record. The stream processor provides your account ID, and the database returns the complete value payload without any heavy relational math. Flink queries Cassandra and instantly retrieves a vital piece of context. You bought a coffee at a cafe in Mumbai exactly 2 hours ago. Because there were no complex table joins, this entire historical context fetch is completed in less than 20 milliseconds. Engineers choose NoSQL over RDBMS in this pipeline to prioritize retrieval speed over relational complexity. It's the only way to beat the clock. Now the ML model has everything it needs: the current withdrawal attempt in Moscow combined with the Mumbai coffee purchase from 2 hours ago. This specific data mismatch triggers a calculation known as impossible velocity. This map tracks the physical distance between Mumbai and Moscow. The model calculates the exact travel speed required to cover that distance in 120 minutes. The required speed far exceeds commercial aviation. You cannot physically be in both locations. Based on this mathematical discrepancy, the machine learning model scores the Moscow ATM transaction with a 99% probability of being fraudulent. The stream processing engine receives this score and generates a hard decline command payload. That decline message is fired back out of the stream processor through the bank's secure infrastructure and back to the Russian ATM. Advanced machine learning algorithms are dependent on the underlying data engineering pipeline to deliver their inputs exactly when they are needed. Look at the complete pipeline. The packet leaves the Moscow ATM, hits Kafka, moves to Flink, pulls Cassandra context, runs the impossible velocity inference, and shoots a decline command back to Moscow. The timer stops at exactly 2.5 seconds. The SLA was protected. The machine flashes transaction declined. The hacker in Russia walks away empty-handed. You in India continue sleeping because a network of distributed systems just secured your account. This 2.5-second sequence repeats millions of times a day, operating silently across the globe to secure the digital economy. Data engineering provides the architecture for these mission-critical systems where latency determines the success or failure of a transaction. It moves the focus from simple data visualization to building high-availability infrastructure that guards millions of accounts. If you are an engineer watching this, this is the ceiling you should be aiming for. Move beyond basic SQL scripts and start thinking about latency, master stateful processing, and massive distributed architectures. To help you level up and build these pipelines yourself, hit that subscribe button to join 2 Layman Data Engineers. We'll see you in our next data story.